Okay, so today we are going to study quantum superdense coding. Well, sounds like a fun name, but we'll get to it and we'll do it a bit slowly. So, we've been studying quantum entanglement, and the question is the following. Can we use entanglement for communication? And let's say Alice and Bob uh, share an entangled state. Now the idea is, so this is Alice, this is Bob, and there's a state shared between two of them. One qubit Alice has, the other qubit Bob has, and this is a joint state. Now Alice wants to send Bob two classical bits of information. Let's say A and B. So, how does Alice do this using this quantum state? How does Alice accomplish this? So, uh, see, the idea is that Alice will have to send her half of the qubit to Bob, and by sending this one qubit, we need to accomplish this task. Alice needs to transmit 2 bits of classical information. So, let's see what I'm trying to suggest, and then I'll convince you that this indeed works. So, this is A and B. Well, what can it be take? I mean, these are the values it can take: 1, 0, 1, 1, 0, 1, 0, 0. These are the possible information that Alice needs to send. So, Alice applies Z operator if A is true, if A is true or A is 1. Alice applies X operator if B is true. So let's see what I mean by this. Essentially, let's say this was the initial state. We had okay, and I have A, B. Let's say I had encoded. So if both A and B are 0, Alice does nothing. Alice just sends the state as it is. So if A and B both are 0, Alice is sending Bob size 0, 0. Now if Alice wants to send 0, 1, what does it do? Well, consider this psi 0, 1, which is obtained by just putting an x operator uh, on x Alice on psi 0, 0, and that's going to give me 1, 0 plus 0, 1. Just flipping the first operator. If Alex wants to send, so this was taking into account 0, 1. Alice applies the x base to 0, 1. 1, 0 would be if Alice needs to send, so ultimately if Alice requires to send 0, 1, it's going to send Bob this state, psi 1, 0. That would be just obtained by locally hitting it with the gate x naught and then sending the state over to Bob. Now, if Alice wants to send 1, 0, it's going to apply the z operator to the initial state shared by Bob and Alice, and that's going to yield 0, 0 minus 1, 1, and going to send it to Bob. So I'm just going to say this is Alice, somewhere there is Bob. You get the point. So I'll say this was, Bob is, yeah, so this was for sending 1, 0. I'll just mark it down at here. A, B, over here. A, B. And all these states are being sent to Bob. Bob already had a qubit. Alice is just applying this gate and sending the whole state to Bob. So the Bob is now going to contain this state. Similarly, for if Alice wants to send 1, 1, Alice is going to apply x as well as z, and it's going to send 1, 0 minus 0, 1. So these are the Bell states. After applying this local operation at the Alice's end, A stands for Alice, Alice is going to send her half of the qubit to Bob, and Bob is going to have either of these states. Now, 3. Once Alice has sent her qubit to Bob, Bob has one of psi 0, 0, psi 0, 1, psi 1, 0, psi 1, 1. And he can distinguish them. Once he can distinguish these states, Bob automatically knows either Alice sent 0, 0, 0, 1, 1, 0, or 1, 1. Now, why? How can Bob distinguish them? What uh, aspect of quantum mechanics will help Bob distinguish them? Why can Bob distinguish these 4 states? Well, if you look at it, these 4 states are orthogonal. Are orthogonal states, and think about it, but the idea is that one can always distinguish orthogonal states. Well, to see this, lambda 1, let's say lambda 1 was the first state, lambda 2 was the second state, lambda 3 was the third state, and lambda 4 was the fourth state. Well, one can always think of a Hermitian operator where the eigenstates are given by lambdas. One can always think of a Hermitian operator whose eigenstates are lambda i's. So I have an operator A with some spectral decomposition, the following, where lambda I can be any of the eigenvalues distinguishable. And postulate of quantum mechanics tells me that measuring A will collapse the state into one of the eigenstates. So in principle, Bob can have an operator that, like A, measuring this is going to collapse it into one of these four states. So hence these states are actually distinguishable states. So that's the idea. So what's the message? The message of the above protocol is one qubit plus one e-bit. Qubit, by qubit I mean Alice and Bob were sharing an entangled system that was called the e-bit. So one e-bit of shared entanglement plus one qubit of quantum communication. Remember, Alice will send its half of the qubit to Bob after doing some operation. This is 2 bits of classical information. I put this greater than sign here. It doesn't mean greater than or equal to sign in your usual sense. It just means it accomplishes. So that means that one qubit of quantum communication and one e-bit of shared entanglement can accomplish 2 bits of classical information. Remember A and B, 0, 0, 0, 1, 1, 0, 1, 1. So this can be accomplished through a shared entangled bit and one qubit of quantum communication. And this protocol is called as the superdense coding. Basically, the idea is that if I have an entangled bit, then I just need to send one qubit of quantum information to accomplish a task which is communicating 2 bits of classical information. Classical information. This is called as superdense coding. And well, in one of your homework problems, hopefully you're going to manipulate this circuit, but that's the idea. You have essentially, that's how the protocol goes. This is the initial circuit to create the entangled state 0, 0, 1, 1 over here using the C0 gate. And then depending upon what Alice needs to send, it's going to apply either X if B is 0 b is 1. If b is 0, this is just a straight wire because it's x to power of 0. Or z to the power of a and b are classical bits. And I'll have, so this is what Alice does. It sends the state over to Bob, and then this end is basically uh, what Bob is doing. So after sending the state, depending upon what Alice wants to apply, from here Alice has sent the state to Bob, and Bob takes over, and I'll just write it down. This is Bob measuring a Hermitian operator A. So convince yourself. So this is equivalent to Bob measuring. Basically, Bob can measure both the qubits in the Z basis, and depending upon the outcome of Bob, Bob will come to know what are the classical bits which Alice was sending. So state over here is going to be either psi 00, psi 01, psi 10, psi 11, and Bob will make these measurements and conclude what Hermitian operator Bob wants to measure. So we have seen that one E bit, that was a shared entangled bit, and one qubit, which was what Alice was sending to Bob, uh, of quantum communication, can be used to communicate, can be used to communicate two classical bits. Well, the question is reverse also true? Think about it. What do I mean by reverse? By reverse, thinking about reverse, I mean that I give you one entangled bit, shared entangled pair. Let me just write down the page number. One E bit, shared entangled pair, and I give you two classical bits to communicate. The question is that can you transfer one qubit of information? That's the question. So notice this is a very interesting problem, and it doesn't look as trivial. It just looks like the reverse of superdense coding. Superdense coding, I had one E bit and I had one qubit of quantum information, and which I was allowed to communicate, and I was able to send you two classical bits, A and B. Over here, I have one E bit, the same entangled, shared entangled pair, and I give you freedom to communicate two classical bits. Alice can communicate two classical bits to Bob. The question is, can it communicate one qubit of information to Bob? Now, this is something very interesting. See, because one qubit is what? One qubit is, let's say, C10 plus C21. I can normalize it, but essentially that's the idea. I have to send you C1 and C2, two complex numbers. In some sense, this is sending infinite information, because to specify exactly C1 and C2 requires precisely to all decimal places is infinite information. So the idea is that using one shared entangled bit and two classical bits, can it accomplish sending one qubit exactly, which in some sense is sending infinite information. See, because if I have, and mind you, this is also an unknown qubit. I am going to send an unknown qubit. That's the beauty. We'll come to that later. But essentially, the idea is I give you a state psi to Alice. Now, using one E bit between Alice and Bob and two classical bits, Alice has to send this state to Bob, and this protocol doesn't even require that Alice has to know the state, so it can send an unknown quantum state to Bob using these resources. So we'll be doing that in the next class. This is known as quantum teleportation, one of the very celebrated results of quantum information science. Quantum teleportation. And by teleporting, I mean, what does teleporting mean? So in this case, teleporting means I am sending an unknown quantum state. So I'm going to draw the circuit diagram of teleportation. We are going to take it in the next class. But before the next class, just play around with it and convince yourself that actually it does accomplish the task. So this upper wire is the psi, the state I want to submit. And I have these two qubits. I have three lines. So I have essentially the last row belongs to Bob. So first I am going to have this, I'll make this circuit. I have the C0 gate. I start with 0 state. I have a Hadamard gate applied here. I'll have a control knot here. I have a Hadamard gate here. Let me just draw the circuit first. And yeah, now I am basically essentially, this is a Hadamard gate again. I'm going to measure these two wires. Depending upon whatever results I get, A and B, these are, remember, the two classical qubits I want to send. These are classical wires. And depending upon the value of A and B, I am going to apply two gates. Sorry. So in this circuit diagram, yeah, so this is also 0. This last wire is Bob's end. This is Bob. So idea is Alice and Bob start with an entangled pair. This is the entangled pair. That's one qubit Alice has, the other qubit Bob has. This is Bob, this is Alice. They share an entangled pair, and this is again Alice. Ultimately, at the end of the circuit diagram, the protocol, the state with Alice ends up on the wire of Bob. So Bob receives the state, and in the process, what's happening is that Alice is of course applying a bunch of gates, but more importantly, what Alice is doing is Alice is sending two classical bits of information after measurement to Bob. So these are the wires that communicate A to Bob, B to Bob. Depending upon the values, Bob is applying these two gates, and ultimately after this protocol, we'll find that the state psi, which Alice had, and it was an unknown state, mind you. It could have been any state which Alice also doesn't know. That's going to end up with Bob. So this is the circuit diagram for quantum teleportation, which we are going to take up in the next class. Thank you.